Okay. Okay, it's not recording. So I'm just gonna. Okay, so during last class, we did example 5.11. And so this example we're going to do now is going to use example 5.11 from last class, okay? Okay, so this was the example, the 5.11 from last class. Okay, so I'm just going to copy and paste that over here. So from example 5.11, and that was 5.11. So from that example, what is the probability that more than 3 calls will arrive within a 5-minute period? Okay. So it's given to us that the time interval in minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. So the number of calls from time 0 to t is a Poisson random variable. Okay, with parameter lambda t, and lambda t is equal to 1 over theta times t, and so that's equal to 1 over 0.5 t. Okay, let capital X be the number of calls arriving within a 5-minute period. Okay, so then capital X is a Poisson random variable with parameter lambda, which is equal to 1 divided by 0.5 times 5, because there's 5. It's a 5-minute period, so the t is 5 here. Okay, so you're calling lambda now the parameter instead of lambda t, but the parameter is lambda t, which is 1 over 0.5 times the time, which is a 5-minute period. So 1 over 0.5 times 5 is 2 times 5, which is 10. Okay. Therefore, the probability that more than 3 calls arrive, well, we'll leave out arrive. So more than 3 calls in a 5-minute period. It doesn't matter which 5-minute period, right? So it's uniform. Okay. So every 5-minute period will be the same probability. This is equal to the probability of x strictly greater than 3. Okay, it's because we want more than 3 calls. So we want more than 3 calls. And so if we want the probability of more than 3 calls in a 5-minute period, then since x is the number of calls in that 5-minute period, we want the probability x is greater than 3. Well, that's equal to 1 minus the probability that x is at most 3, right? And so then this is equal to 1 minus. So now we just need to find the probability that x is at most 3. And so to find the probability that x is at most 3, we can find the probability. We can find the probability that x is 0, find the probability that x is 1, find the probability that x is 2, and find the probability that x is 3 and add them up. Okay. So x is a Poisson random variable, right? X is a Poisson random variable. And so that means that its probability function is the Poisson distribution function. Okay. And so you just use the Poisson distribution function where x, the value of x is 0 or 1 or 2 or 3, and 10 corresponds with the parameter, right? So right, okay, so then you have to find those values, and so notes, so a reminder, right? The Poisson distribution function is just p of x colon lambda, and which is equal to this fraction. So you have lambda to the x times e raised to the negative lambda. Okay, and then that's divided by x factorial. Okay, so that's the Poisson distribution function. This is the Poisson distribution function, right? Poisson probability distribution function. Okay, and so that's what we want to use here to calculate the probability that x is 0, 1, 2, or 3. And you add them up, and that's the probability x is at most 3. And so you calculate this value for each of those, and you plug them in. You add them up, and you subtract it from 1, and you're done. So for instance, the probability of 0 colon 10, you would just plug in those values. So you have the fraction here that lambda is 10, right? So for 10 here, you would have 10, and you would raise it to the x power, which is 0, and then it would be e raised to the negative 10 divided by x factorial, which is 0 factorial. And remember, 0 factorial is 1. And so, reminder, 0 factorial is 1. Okay, so here we have 0 factorial, it's 1. 10 to the 0 is 1. So this is the same as e to the negative 10. Okay? And so here, when you calculate all those values and you add them up and you subtract it from 1, you get 1 minus 0.0104, and that's equal to 0.9896. Okay, and so that's the probability of more than 3 calls in a 5-minute period. We have a Poisson random variable, and so we use the Poisson probability distribution function. Okay, and we're given lambda. Okay, so there we go. We're given the parameter, right, which is lambda t. And so now that you're talking about it with the parameter, now you're just going to call them, you're going to reuse, it's called abusing notation, right? So you use lambda here in order to get the parameter for your random variable, but now that's the new lambda. So the new lambda is now 10. Okay. Okay, so note, if there are on average lambda events of a certain type within a unit time interval, then on average, time between events will be theta, which is equal to 1 divided by lambda. Okay, so in other words, if capital X is an exponential random variable with parameter theta, then on average, the observed value of capital X will be theta. Okay, so for example, if time in minutes until an accident after 4:30 p.m. Is an exponential random variable with parameter theta is equal to 15, then on average, that time is 15 minutes. Okay, good. Okay, so let's go to the next section. So 5.7.3, which is the normal distribution. Normal distribution. Okay, so let me just move this down. Okay, so a normal is a continuous random variable, capital X, has a normal distribution and is a normal random variable if its probability density function is defined as follows. Okay, so a continuous random variable capital X has a normal distribution and is a normal random variable if its probability density function is defined as follows. So definition. Okay, let mu and sigma be constants with negative infinity, strictly less than mu, strictly less than infinity, and sigma is positive. The function f of x, which is equal to 1 over 2 pi, oops, okay, let's do it this way, square root of 2 pi sigma. The sigma is not under the square root, so I'm just going to put a space here. It's still in the denominator, just so you see it's separate from the square root. So f of x equals 1 over the square root of 2 pi times omega times sigma in the denominator times e raised to the negative x minus mu squared, but still in the denominator, is divided by 2 sigma squared. And this is for negative infinity strictly less than x strictly less than infinity. Then that function is called the normal PDF with parameter mu and sigma. Okay, so let mu and sigma be constants with mu finite and sigma positive. The function f of x, this function for any real number x, is called the normal PDF with parameter mu and sigma. Okay, so if your PDF for a continuous random variable is this, then it's a normal random variable. Okay. Okay. So I'm going to draw the graph of this function on the whiteboard. So it's often called the bell curve. Okay, so it looks like that. Okay, this is mu. Okay, this is f of x. This is the graph of y equals f of x. It's curved on the xy axis. Okay, and so that's called the graph of the normal PDF function. Okay, and so the normal PDF is the most important PDF in probability theory because it models the most situations in the real world. Okay, so I'm just going to write it down. The normal PDF is the most
enfocada la conversación.
PDF.
Ay, eso es profunda la vaina. Hay problema.
Without question, because it models the most real world situations. Good. Okay, so that's the normal PDF. So it's a continuous random variable whose probability density function is that. So 5.7.3.1. Finding the probabilities. Finding probabilities for normal random variables. Okay, so the normal PDF does not have an antiderivative. Okay, and so we have to rely on tables for its values. Okay, so in the book that this class is modeled on, it's table 3 in Appendix C. And so since that was needed, I included that on Blackboard, right? So when you go on Blackboard, there's a way to see this table. And so I'll show you now how, once I write this down. So table 3 in Appendix C has values of the probability that 0 is strictly less than x, strictly less than z, okay, for normal random variable capital X with parameter mu equals 0 and sigma equals 1. And it's called the normal, it's called the standard normal random variable. Okay. So the normal PDF does not have an antiderivative. So this function here, which is the normal PDF, this function does not have an antiderivative. And so normally when you integrate over a function, when you integrate a function, you use the fundamental theorem of calculus, which means you find an antiderivative of the function and you evaluate from one point to another point, right? You find the difference of the values of an antiderivative from A to B, let's say, right? Okay, so you need an antiderivative to calculate calculate an integral. But since it doesn't have an antiderivative, we rely on tables for its values. So these tables will tell you the values of the integral for ones that you might need. So table 3 in Appendix C of this book for the class has values of this probability for a normal random variable x with parameter mu equals 0 and sigma equals 1. Okay, so table, actually I'm going to underline this whole thing here. So table 3 in Appendix C has values of this probability for a normal random variable x with parameter mu equals 0 and sigma equals 1, called the standard normal random variable. Okay, so when you have a normal random variable, right, you have this function, right? This function is a normal random variable, right? And the only conditions on mu is that it's finite and that sigma is positive. But if you specifically choose mu to be 0 and sigma to be 1, and you plug those values into this function, so mu is 1 here, so that's a 1 there. There's a 1 here. Sigma is 1 here, sigma is 1 squared there, and mu is 0 here, so it's x minus 0 squared. So if you plug in those values, the f of x you get is 1 over the square root of 2 pi times e to the negative e to the x squared over 2. Okay? Okay, wait. Oh, sorry. There's a negative sign here. I thought I wrote that in. Apparently I didn't. Okay, so there's a negative sign right there. See that negative? I just put that there. There's a negative sign right here. Okay, I just added it. Okay, so so the PDF, that is the exact PDF. Okay. So when you plug in sigma is 1 and mu is 0, you get 1 over the square root of pi times e to the negative x squared over 2. And so that's the PDF for the standard normal random variable. And it's the values of the probabilities for that PDF that's given in the table. Okay. So your first question is probably, how do you find the probability then of a normal random variable if you only have a table for standard normal random variables? And so the answer is that there's a way to convert the probability of a normal random variable to probabilities of standard normal random variable. Okay. And so in some problems, the first step will be to convert your probability of a normal random variable to the probability of a standard normal random variable. And then once you've done that, you can use the table. Okay, so we'll see that. So another important fact is that the probability of negative z is less than x less than 0 is equal to the probability that 0 is less than x less than z. Okay, and so that's true. Okay, and so this is true because the standard normal random variable is symmetric about the vertical axis, x equals 0. Okay, so what does that mean? So remember, for the standard normal random variable, mu is 0 and sigma is 1, right? Mu is 0. So here, mu is 0. If this is 0, right, that means the x value of mu is 0. That means you have a bell curve where the y-axis is an axis of symmetry, right? That means that means the right and left side are mirror images of each other. Okay, And so if you wanted to find the probability, if you wanted to find the probability from negative z to 0, right? It would be the area under this curve from negative z to 0. But that probability would be the same as the if you said flipped it, the negative z to z, or z to negative z, right? You'd correspondingly be looking at this half on the other side. And because it's symmetric about the y-axis, this red area is the red region takes up the same amount of space as the blue one. And so the probability that x, your standard normal random variable, is between negative z and 0 is the same as from 0 to z, because this symmetry about this y-axis. Okay? Right? And so this blue region here is the value of the definite integral from negative z to 0 of your PDF. Make sense? So it's the value of that definite integral, which is the value here, and that's the same as the value of this definite integral from 0 to z of f of x dx. Okay, so we have this symmetry going on here. So let's go back to here. Okay, so that's what I was explaining there. Okay, so let's do an example. Okay, so example 5.15. Let capital X be a standard normal random variable. Use table 3 to find the following. So I'll show you where this is. The probability that 0 is less than x less than 2. B, the probability that negative 2 is less than x less than 0. C, the probability that negative 1.5 is less than x less than 2. And E, probability that x is strictly greater than 1.14. Okay, so for example 5.15, we want to find these 4 probabilities, given that x is a standard normal random variable, because that's the only information we have. And so with just that information, we can use a table of values to find those probabilities. Okay, so let me get the table on the screen. So I'm going to stop sharing for a second, so I can switch to something. Okay, so it should just take a minute. Okay. Okay, good. Okay, it's all ready now. Okay, so I'm going to go to screen share, and I'm going to go here. So if you go to course materials right here, so you're on the page, right? So you're on the page, and you look at the menu bar here. And so if you go to course materials, it's titled Table 3 Appendix C. Okay. So I've considered changing the name, but it goes with if you were to get the book, that's the name of the table, and in the lessons I refer to it as Table 3 Appendix C. So if you click this, it will then bring up the file. It's like scanning to make sure that my own file doesn't have a virus. Okay, and so then you'll get this. Okay, maybe you don't want to enable editing, right? Because you don't want to change the table, right? So do you see that on the screen? No. Okay, here it is. So I double click that. I clicked that on Blackboard just once, right? And then here are the table of values. Okay, so I inputted them manually. Okay, so it was in a book, and then you don't have to buy the book anymore. So I inputted all 2, 4, 6, 8, 11 times 32 cells into this table, onto this Excel document. So that's over 300. That's like 380 something cells, right? So almost 400, at least 380 cells are in this table. So I input them one at a time with 4 decimal points for each one correctly. So, okay, so you now have this table of values. Okay, so don't change the table, but if you do, you can always just re-click it on Blackboard if you make a mistake, right? But if you accidentally change the values here, it does affect the answer, right? So you don't want to change the values on this table, right? So the entire class will be referring to these values on this table. Okay, so as long as you're using the table I posted on Blackboard, I don't know. Maybe it took an hour or 2 hours. I don't know. I can't remember. I did a little while ago. This isn't the first time I taught this class online, so I did it for the first time I taught online, and it was something. Okay, so this is the table we're going to refer to. So let's go back here. So let's start off with part A. So for part A, you want to find the probability that x is strictly between 0 and 2. So using using table 3, we get that the probability of 0 less than x less than 2 is equal to, and so let me explain how the table works. So 0 less than x less than 2, right? So we want 0 less than x less than 2. So z is the 2. Okay? So it explains it here in this short little thing. Standard normal probabilities table. The probability of 0 less than capital Z less than little z for given values of little z. Capital Z is the standard normal random variable. Okay? It's not the letter Z that matters. It's what Z represents that matters, right? So in this problem, capital X is a standard normal random variable. So here I'm using Z to represent, that's the standard notation for it. But there's no one set notation. Some problems will use different letters. Okay, so the X in this problem is our standard normal random variable. And so in the table, the X the X in the problem is being referred to as Z on this table. Okay. So capital Z is the capital X of the problem, right? And so this table is telling you what is the values that capital X, which is called Z here, is between 0 and little z. So in the problem for A, we want the probability that 0 is less than x less than 2. So little z here is 2. See that if you match that up, probability of 0 less than x less than 2. So z here, what you want is z equals 2. Okay? And so this whole table, you just fish for 2, but it's in order. So if you go here, you go down to 2. See how you have 2 here? There's a 2 there. Nice and simple. And then I don't just have 2. There's fractions of 2. So 2 and a 0. A 0 means there's no decimal afterwards. So 2 and 0 means 2.0. So the probability that 0 is less than capital Z less than little z equals to 2.0 is 0.4772. See that? Right there? The probability that 0 is less than capital Z less than z equals 2 is 0.4772. That cell right there that I just highlighted. That's 2.0. Okay? So then back in the original problem, you would say that this probability is equal to 0.4772. And that's the answer to A. Okay? Nice and simple. B, what is the probability that -2 is less than x less than 0? Well, we had the symmetry equation earlier. So this is equal to the probability that 0 is less than x less than 2. Right? Just above over here, right? If you can, instead of negative z to 0, it's 0 to z. So instead of negative 2 to 0, it's 0 to 2. But we've already found that probability. And so it's equal to 0.4772. Okay. And so B brings up a good point, that the table will only tell you values between 0 and a number, right? 0 and 2, let's say, right? It won't tell you between -5 and 1. But remember, the probability of negative to 0, a negative of a number to 0 is equal to the probability of 0 to a number. And so from just the probabilities in the table, you can then engineer your given probability as maybe a sum or difference of probabilities in the table. Okay? So there's a way to express your given the probability you want to find as maybe a sum or difference, or you might have one minus or something, right? So there's a way to translate the probability you want to find to the probabilities of this form, which are all in the table. Okay? And so in this case, we use symmetry, and we see the probability you want to find is equal to this probability, which is in the table. So it requires a little bit of creativity, but it's, if you do enough of these examples, there's only so many ways that this kind of a problem will offer any kind of difficulty. Once you've done enough of them, there can't be a surprise. Okay, as long as you've seen all the surprises that could happen. So the probability that x is between -1.5 and 2. Before we look at the table, right, we keep in mind that we know the type of probabilities that the table has, right? X strictly between 0 and some number. So we need to get that of this form. So that probability is the same as the probability of -1.5 less than x less than 0, plus the probability of 0 less than x less than 2. Okay. Now, technically, there's x equals 0, which I didn't include, right? You see that? But remember, this is a continuous random variable. And so the probability that x is equal to any fixed number is 0, right? So if we include or don't include single points, it will not affect the probability. Okay. So now you see how this probability is the same as this plus this, where x equals 0 was removed, but it doesn't matter because that probability is 0, right? So having a probability of 0 or not having it makes no difference, right? Okay, so now let's use symmetry again. So whenever you have negative to 0, you go 0 to positive, right? But this was no coincidence. We chose to stop at 0 so we could flip it, right? So we made that happen. So we made that symmetry happen by how we split up this probability as a sum of two probabilities. And so that's no coincidence. So this probability is the same as this one by symmetry about the y-axis, and that's the same. And so now we have our original probability as a sum of two probabilities that are available in the table. This probability and this one. Okay? And so the question now is, what is the probability that capital X is between 0 and 1.5? Okay, what is that probability? I'm going to save. Okay, so let's look at the table. Did you have the Word document this whole time? Or no? I hope you had seen this. I hope this was on the screen while I was talking. So A, B, and C, right? I just did. And I'm hoping you could see that while I was doing it. Now going to the table. Okay. So we need it from 0 to 1.5. So from 0 to 1.5 means little z is 1.5, which means that's the value. It's 0.4332. Okay. So the probability that of 0 less than capital Z, our standard normal random variable, less than 1.50 is 0.4332. All right. And so it's this is equal to 0.4332 plus the probability of 0 less than x less than 2, which we already found and we're going to use again, 0.4772. Okay, and so now you just add those two up. You can use your calculator if you want. You have 0.9104. Okay, so then that's the probability for C. And now for D, what is the probability that capital X is strictly greater than 1.14? So we want to find that probability. So my first thought is, well, let's do 1 minus the probability of X less or equal to 1.14. Right? Well, that probability is equal to 1 minus, and sometimes I'll do this, I'll put a bracket here, and now whatever I put in the bracket is the probability I'm subtracting, because you don't want to forget that you're subtracting this whole probability. And so if you're expressing this probability as a sum or difference of probabilities, you have to keep in mind that because you're subtracting that probability, if you substitute, you'd be subtracting a sum or difference, and that negative sign is supposed to distribute, right? And so if you get a bunch of terms here for this probability, by putting a bracket around it, you're reminding yourself that, okay, I'm expressing this probability a certain way, but I still have to negate it. I still have to distribute this minus sign to all the terms I'm going to put here. Okay, so I put a bracket there to make it easier. And so this is the probability that capital X is less or equal to 0 plus the probability that 0 is less than x less than or equal to 1.14. Okay, see that? So for x at most 1.14, it's either less or equal to 0 or strictly or greater than 0 and less or equal to 1.14. Okay, just one decimal there. Okay, so the right probability is from the table, and I chose this one because this is 1/2, right? Remember the symmetry about the y-axis, right? The symmetry about the y-axis, and so half of the space underneath the graph is on one side, the other half is on the other, and so if the entire area has to be 1 because it's a PDF, and so if you add up, infinitesimal, the probabilities on the entire real line, the entire area under the bell curve has to be 1. And so since the y-axis splits it into a right side and a left side, and the entire space under the graph is 1, that means the entire area on the left side of the graph is 1/2, and the entire area on the right side of the graph is 1/2. And so the probability that x is at most 0 is 1/2 due to that symmetry. Okay, and so then this is again not an accident. I chose to split it up this way. That way I could say, okay, this is 1/2, and then plus this probability. Okay, and so what is the probability that x as a standard normal random variable is greater than 0 and less or equal to 1.14? Well, then we refer to the table. So we go to the table and we have 1.14. So 1.1 is here, right? So you got 0 less than our standard normal random variable x, less than 1.14. So little z is our 1.14. So this is 1.1, but don't worry too much. Now I'm just showing you what to do here. You need in the hundredths place a 4, right? Because you need a 1.14. So this is how the table works. These values are hundredths, okay? So the first column would be 1.10. This would be 1.10. This would be 1.11. This would be 1.12 because it's adding 2 hundredths to 1.1. This would be 1.13 because you're adding 3 hundredths to 1.1. This would be the probability of 0 less than z less than 1.14 because you're adding 4 hundredths to 1.1 and so forth. So this would be 1.15, 1.16, 1.17, 1.18, 1.19, And then you see the next row, you would just end up at 1.20, 1.20, 1.21, 1.22, 1.23, 1.24, etc. Right? And so you see how this table exhausts all the hundredths. Okay, starting at 0 and going up to and including 3.99. Okay. No, wait, no, not that much. Wait, 3.00. This goes up to 3.09. Okay, so it goes from every hundredth from 0 to 3.09. So I guess that's 309 cells. I mean, when I counted the first column and the first row are indices, they're not part of the values. Okay. Okay, so the one we want is 1.14. So it's 1.10, 1.11, 1.12, 1.13, and then 1.14. Okay. If you use the toggle bar on your computer to move around, which might actually make it easier, just be careful because you don't want to accidentally press a number and change one of the numbers in the table. Right. So this is 1.14. I think you can tell it to not edit it. Right. You can put in non-editing mode or something, where you don't allow yourself the ability to edit the table while you're using it. Okay, so this is 1.10, 1, 2, 3, 4, 1.14. Okay, and that's what we want. And so it's 0.3729. 0.3729. And so here you have 0.3729. Okay, so I put a 1/2 here, right? And so I guess since you have a decimal, you could put a 0.5 here. Decimals are not as nice as decimals are not nice as fractions. You might think the other way around, but fractions really visualize the concept that they're illustrating, right? 1/2, when you see the fraction 1/2, it looks like 1/2. When you look at 0.5, you see a 5, and so somehow a 5 represents a half, right? So 1/2 is much easier to understand as being the thing it represents. But so I automatically initially write down the fraction, but that's 0.5 because it's a half, right? So since we're adding decimals, I'm going to put it as a 0.5 there. Okay, so this is equal to 1 minus in the bracket 0.5 plus that. So that's, you can add 0.5 to the tens place for this one. There's no carryover of digits. So you get 0.8729. It's a minus sign here. All right. And so it's 0.8729. And then that's equal to, so it's 1 minus that. And so you get 0.1271. And that is the probability that capital X is greater than 1.14. Okay. Okay, so we have that there. And so that entire example is now done. What we did was we let X be the standard normal random variable, and we used the table 3 to find those 4 probabilities. Okay, so next, if capital X is a normal random variable with parameter mu and sigma, parameters mu and sigma, then plural parameters, then Z is equal to X minus mu over sigma is a standard normal random variable. Okay, so if you're given a normal random variable, right, the table only applies for standard normal random variables with parameters mu and sigma. So if you're given a normal random variable, capital X, then in order to capital X, then in order to find a standard normal random variable, you define it as Z equals X minus mu over sigma, and now you have a standard normal random variable. And so that's a way to convert a normal random variable to a standard normal one. Thus, to find the probability that A is strictly less than X, strictly less than B, we do the following. Okay, so this is an important thing to highlight here. So I'm going to move this down. In fact, I'm not just going to move it down. I'm going to like section it off, which is what I do when I want you to focus on a particular part of the lesson. Okay, so if you want to learn how to do this problem, look at what's in between these two lines, and then the explanation's pretty much there. Okay. Okay, so I'm going to keep writing in between these two lines. Thus, to find this probability, we do the following. So the probability that little a is less than capital X, less than little b, is equal to the probability that a minus mu over sigma is strictly less than X minus mu over sigma, which is strictly less than B minus mu over sigma. And that's equal to the probability that A minus mu, A minus mu over sigma is strictly less than Z, strictly less than B minus mu over sigma. Okay, so here, it's right there already. Okay, Z is equal to X minus mu over sigma, right? And so here's this is a capital X. Okay, so I just take each of, if you want to find the probability of X being in this interval, capital X, your normal random variable, then the values of capital X that satisfy these inequalities doesn't change if you subtract each of them by the same mu. And then you divide all of them by the same positive sigma, right? Sigma is required to be positive already in the conditions for a normal random variable. So dividing by sigma will not change the direction of the inequalities. When you divide by a negative, it switches. When you divide by positive, the direction stays the same. So dividing each of them by sigma after subtracting by mu doesn't change the sign. And so the capital X that satisfy this inequality are the exact same values of capital X that satisfy those inequalities. And so we're finding the probabilities of the same set of X values here, okay? So it's a probability of a certain set of X values equals the probability of the same set of X values. So these two probabilities are equal. And then Z equals X minus mu over sigma. That's the middle term. So the probability of X satisfying these two inequalities is the same as the probability of Z equal X minus mu over sigma satisfying these two inequalities. Okay, so this probability in terms of X is equal to this probability in terms of Z. Okay, so I've defined Z as X minus mu over sigma. And so certainly from these two equations, you see that this probability is equal to that one. The added point that I already made is that Z is a standard normal random variable. And so it turns out that this Z is, in fact, if you have any normal random variable X and you subtract it by mu and divide it by sigma, you get a standard normal random variable. Okay. And so that means that the mean for Z is 0 and the sigma is 1. Okay, and so here, so this probability using table 3 in appendix C, you can calculate this probability. Okay, so now that Z is a standard normal random variable, and we want to find the probability that a standard normal random variable is between these two values, you can use appendix C to translate this into probabilities in which the table gives you values for. Okay, so you can use the table to find this probability. So first you notice this probability equals this one. Then you translate this into probabilities, which you can get from the table for a standard normal random variable, Z, and then you find this probability using the values of maybe several probabilities from the table. Okay, and so that is the method to do these kind of problems. And so it's put in between these two bold lines here. Okay, so now we're going to do an example where we do with all of that. So this is example 5.16. So for example 5.16, let capital X be a normal random variable with parameter mu is equal to 2 and sigma is equal to 0.5. Find the probability. Find the probability that 1 is strictly less than x, strictly less than 2.1. Okay. This is your capital X. Capital X here is a normal random variable, right? It is not a standard normal random variable, right? The table gives you values for a standard. See the word standard? Is capital Z in this table is a standard normal random variable. So you cannot go directly to the table to calculate this probability by expressing it as a sum of two sum or difference of probabilities. You have to first convert this probability of X into probability involving a standard normal random variable, which we will call Z. Okay, so define a standard normal random variable by the equation Z, capital Z, is equal to X minus mu over sigma. That's what you always do. Okay, so whenever you need a standard normal random variable and you have a normal one, just set Z equal to X, your normal random variable, minus mu over sigma. Okay, so that's now, this is your standard normal random variable. Now, X is over here from this. Now, mu is 2, right? And sigma is 0.5. So Z, the standard normal random variable that you're defining yourself, Z is equal to X minus 2 over 0.5. Okay. So I'm just going to put, these are the steps involved in doing this problem. So step 1 is define a standard normal random variable using mu and sigma, using the given values of mu and sigma from a normal random variable. Okay, we have a normal random variable X. we have the mu and sigma for it, and I will use those values to define a standard norm random variable. That's step one. Step two is use the fact that okay, so use the fact that the probability that A is less than capital X less than B is equal to the probability of what I wrote before, A minus mu over sigma is strictly less than Z, strictly less than B minus mu over sigma. Okay, so define a standard normal random variable, say you call it Z. You may have to call it something else depending on the context. Here I'm going to say it's Z using the given values, right? And so now here, use the fact that this probability is equal to this probability of values of capital Z. So I did that up here. That's from here. Okay. So use the fact that that's true okay, so use the equation that equals that. Substitute values of mu and sigma given to you, right? So if you know mu and sigma, you can plug them in. Maybe the values of mu and sigma and A and B. So mu, sigma, A, B given to you, right? So you may be given mu, sigma, A, and B. And so you'll just have probably of some number less than Z less than another number. Okay, and then step three would be is separate. We express this probability after you've express that probability, and keeping in mind you may now have Z strictly between two numbers, right? Because you substituted A, B, mu, and sigma, right? So express that probability as a sum or a difference, as an expression involving probabilities that you can find in the table 3 appendix C. Find in table 3 appendix C. Okay. And then step 4 would be substitute the probabilities, substitute the correct probabilities. If you put in the wrong probabilities from the table, you get the wrong answer. Substitute the correct probabilities from the table, and then calculate the final answer. Okay, so those are the 4 steps for this kind of a problem. Okay, so I outlined them right here for you. I'm going to put another line here just to separate that. Now the line is not the other page, and I'm going to make the line join the party over here on table on page 5. Okay, so now we have the 4 steps in between those horizontal lines. Okay, so those are the 4 steps, and I'm just going to do those steps over here. Okay, so we defined our standard normal random variable by this equation. That's step 1. Okay, so I plugged in the given mu and sigma here. Okay. Now use this equation, right, and substitute the values of mu, sigma, a, b given to you. Right. So now we have this, and so this is equal to. So here A is 1, B is 2.1. So A is 1, B is 2.1. Makes sense? And then mu is 2. Mu is 2, and sigma is 0.5. So I'm putting a 0.5 here and a 0.5 there. And so now you have that probability. So this is equal to the probability. This is equal to the probability that this is -2, strictly less than z, strictly less than 0.2. Okay, 2.1 minus 2 is 0.1. 0.1 divided by 1/2 is 0.2. 0.1 divided by 1/2 is 0.1 times 2, which is 0.2. So then, so now you have equals to this probability. So then, so that's step 2. Okay, so this was step 1. Step 1 is done here. This is step 2 is done. Okay, and so now we have this probability. So step 3 is express this probability as an expression involving probabilities that you can find in table 3, appendix C. Okay, so now we need to keep going. And so now this is equal to the probability that -2 is less than z less than 0, plus the probability, that's a capital P there, plus the probability that 0 is less than z less than 0.2. And the probability of z equals 0 doesn't matter because it's a continuous random variable, and probability of any one particular value is 0. Now the probability that z is from -2 to 0 is the same by symmetry as 0 less than z less than 2. And then plus the other probability, plus the probability that 0 is less than z less than 0.2, right? I almost looked over the thing. I was like, what? But it's 0.2 here. 2 here, 0.2 there. And so in part 3, in step 3, you wanted to express it as an expression involving the probabilities you can find in the table. And so that we're now done with step 3 is done. Okay. So now that's step 3. So line up these step 3s, these steps on things. Okay, so now you just use the table to plug in the values of those two probabilities, where P, right, is a standard normal random variable. Z is a standard normal random variable. So we want 0 to 2. So the table for 0 to 2, we use this number already. I think we have 0.4772. So you have 0.4772. I'll do the next one slower. This is from 0 to 0.2, right? 0 to 0.2. So now we'll go to the table. It's from 0 to 0.2. So it's that cell. See, 0.2, 0.20. So 0.20 for Z for the number is 0.0793 is probably 0.0793. So this is plus 0.0793. Okay. You can also print the table if you want, right? If you find the table online, you can print it, and then you can have it in front of you, so you don't have to keep going back to it. Also, so that you know you don't change the table accidentally. Maybe you feel more confident that the table was undisturbed if you printed it out, while making sure not to change the table before you printed it out. Okay, so this is 0.55 6.5. Okay, and so then that's, so you just add those two up and you get 0.5565. And so that's the probability for that example. Okay, and so that covers that. And so next time we'll do one more example involving this kind of a calculation. It'll have a part A and a part B. And then we will start 6.1, which means we'll start chapter 6. Okay, let me quickly look and see if I want to assign a homework based on where we are. So the last, I assigned homework 5. Homework 6, I also, wait. I assigned homework 6, right? Right? I assigned homework 6. So I feel like I've assigned homework 6 already. So let me just see something here. Yeah, okay, and we went over it too. So I assigned homework 6 and we went over it. So the next homework is homework 7. And so homework 7 is on 5.7. Okay, so I'm going to assign this homework, but it's not going to be due. Is this on the screen? I'm going to put it on the screen. Okay, so I'm assigning homework 7, but this will not be due until next Wednesday. Okay, so this is going to be due on the 28th, a week from today. Okay, we have a little bit more to do, but I can assign it now because you can pretty much, you could do this now, but it'll be due next Wednesday. Okay, so I'm going to write that down here, and then class is over. Okay, so lesson 20 notes. Oh, these are the steps. I put them. Don't get rid of the line. Okay, so those are the steps involved in the problem. And then, okay, so now, so the lesson is done. Next time, we will finish this section and start chapter 6. Okay, so I'm assigning homework 7. Okay, so I'm assigning homework 7. It is due next Wednesday, week from today. Okay, so next Wednesday, 4/28/2021. I like the dots. Okay, so it's due next Wednesday on the 28th. Okay, and so have a good night. Okay, so that's it for this class. Thank you for coming to class. I'm posting the videos online on YouTube on my channel, Michael Pendazis. So if you want to see these lessons again, there's now a whole bunch of them on YouTube. Okay, Blackboard's not allowing me to post them, so I've started putting them on YouTube. Okay, have a good night. You're welcome. See you next week, Monday. You're welcome. Bye. Okay, bye.